All right. So our project is brain MRI segmentation, and we're team 142. So brain tumors, as I'm sure most of you know, they are essentially abnormal cell growth in the brain or spinal cord region, and they're very prevalent. There's over 25,000 of these malignant or cancerous brain tumors or spinal cord tumors diagnosed in the U.S. in 2023. So they're still a very prevalent issue. They're increasingly so, and thus it's important for us to be able to image those and see them. And we do that with MRIs or magnetic resonance imaging. It's a way for us to see those tumors in the brain, and importantly, where they're located, because that kind of determines how we're going to classify those tumors. It's often by the tissue in which those tumors originate. And all that being said, it's really important that we find out type of tumor, where it is, how far along it is, because doing so allows us to expedite treatment and save people's lives. And thus comes the motivation for our project, which is to leverage deep neural networks in order to perform segmentation on brain MRIs. There's an example of an MRI on the right. What we want to do is we want to be able to classify these images into 4 different classes, a control class of no tumor, and then 3 different types of tumors listed here. So the data set we're using is directly from Kaggle. If you look up brain tumor classification MRI, it'll pop up probably the first result. And we're having to resize those images. This is around 3,000, but we have to resize them to an appropriate input size for our model. But yeah, there's an example of each of those classes there at the bottom and the output there, output distribution. So the baseline architecture we're using is ResNet 50 with transfer learning. So ResNet 50 is a very big residual neural network that's been trained on these huge data sets, and it's very good at its job. It's very good at feature extraction. So just to give a visual here of what's going on as an example, what we're doing is we're taking a model, ResNet 50, that's very, very good at extracting features. But instead of using it to classify on those big image data sets, we're adding a classification head onto the end of it and then classifying into things that we want, like those 4 tumor types. So that's what's going on with transfer learning. So it's been trained on the ImageNet data set. That's the weights that we're using for ResNet 50. We've frozen the feature extraction layers so that we're not actually backpropagating through those. We're not changing any of those weights because we don't want to change how it's extracting features. We want to change how it's classifying the kind of results it gets from that. So all we have at the end of this whole ResNet 50 architecture is just a fully connected layer for the baseline. So our training involves a 70-15-15 training, validation, and testing split, and we're using categorical cross-entropy loss for our loss function. Here are the results of the baseline training. The maximum validation accuracy we've seen is 91.2%. You can see the graphs there to see the progress. So when it came to the testing set, we were able to achieve a test accuracy of around 92% using this model. You can see what the model confused for what in terms of classes. But the main idea here is that this is a pretty high accuracy for the baseline. And that's because what we really want to focus on is not a new architecture per se, but optimizing it. So we want to take this baseline model and optimize it using hyperparameters. That's really what our project is. It's a focus on hyperparameter optimization. So we're doing things like data augmentation. We're doing things like taking a classification or taking the classification head and optimizing the number of layers, the number of neurons in each layer, dropout, learning rate, batch size, all of these things, we want to optimize them so that we can get better results. That's what we did. For example, for these 3 cases for the number of neurons in each layer, we iterated through them and we found the highest validation accuracy and moved forward. So for our final model training, we were able to get a validation accuracy of around 95% at the peak, and the training curves are much more smooth, as you can see here. And then the final model testing, we were able to get on a new test set with all the new data an accuracy of 94%. But when we take a look at here, we can see that on the same test set as the baseline model, we were able to achieve accuracy of plus 3% using the final model with all its optimizations. So in conclusion, these optimizations worked. Obviously, they did their job. We do want to go a little bit further, as I mentioned on the slide previous. But yeah, the classification architecture for the classification head was very simple. So we didn't do much with that architecture, but we wanted to optimize what we did have. And then finally, if you want to perform data augmentation optimization, it comes at an immense computational cost. So you got to be careful. But that's all we got. Thank you.